Good afternoon, ladies and gentlemen. My name is Turov. I'm a student of Perm National Research Polytechnic University and engineer of Perm Federal Research Center of Ural branch of Russian Academy of Sciences Photonics Lab. I would like to present the research dedicated to the evaluation of key characteristics of pulsed terahertz time-domain holography, which was carried out with the help of the photonics faculty staff of ITMO University, St. Petersburg. Here you can see the plan of this report. The terahertz spectral range refers to the frequency domain limited to approximately 100 GHz and 10 terahertz, or wavelengths from 1 to 0.1 mm. The relevance of the study of this radiation is justified by the following features. The presence of the broadband pulsed or narrowband continuously tunable sources of such radiation makes it possible to use it in both spectroscopy and obtaining images with spectral resolution. Terahertz radiation is characterized by low photon energy and is non-ionizing, which makes it possible to use it to study biological objects and large organic molecules. Another useful feature of this radiation is that it is capable of penetrating optically opaque materials, which makes it possible to solve the problem of detecting defects not only on the surface of the material under test, but also in its entire volume. In this field of application, research of semiconductors and drugs, the detection of explosives, non-contact security systems, and non-destructive testing are of particular interest. All these features make terahertz imaging a very attractive tool for non-destructive testing with three-dimensional spatial resolution. One approach for obtaining time-domain images has been proposed called pulsed time-domain terahertz holography. This technique provides the possibility of the direct wavefront inversion and subsequent reconstruction of both the amplitude and phase spectral characteristics of the object. Despite the fact that terahertz holography techniques were proposed more than 10 years ago, its key characteristics such as resolution, contrast, and general features of the reconstructed images have not yet been fully understood. In this work, using numerical methods, a detailed study of these characteristics is carried out. The previously described method of pulsed terahertz holography was used to simulate the following process. A one-period terahertz beam with a Gaussian transverse spatial resolution of the electric field amplitude and a plane spatial resolution of the wavefront is diffracted by an amplitude or phase object, and the diffraction pattern is recorded at distance z, for example using an electrico-optical detection. The angular spectrum method is used to propagate the initial wavefront into the z-plane. To assess the dependence of the resolution and contrast, including on the solid angle and the method of its changing, the size of the test object was changed from 128 by 128 to 256 by 256 pixels, or from 20 by 20 to 40 by 40 mm by zero padding. The object allows direct estimation of resolution and contrast, since it contains elements with widths of 1, 2, 3, 5, 6, and 10 pixels. The test object is assumed to be 100% transmissive in white areas and completely opaque in black when used as an amplitude. When used as a phase one, it is assumed to be transparent over the entire area with a refractive index of 1.46 for the entire terahertz spectrum used. In this case, it is considered that the white areas are 110 microns thicker than the black ones, if the thickness is not specified exactly. The difference provides a phase shift of p at a frequency of 3 terahertz. The spectrum width of one period terahertz pulse is in the range from 0.3 to 3 terahertz. To limit the number of parameters in the study, we will turn to the spatial angle of the hologram as the ultimate unitless parameter for the resolution and contrast study. In the case of observing square hologram with side A and area A square from the central point of the object at distance z, the spatial angle can be calculated as in the slide from the top left. But for most of the investigated distances, the expression can be simplified. Another important parameter is the number of pixels available in the recording plane and in the object plane. Two fundamental limitations of different nature follow from it. Physical, given by the spatial angle and therefore by the covered spatial frequencies, and numerical given by the number of pixels in the hologram. To distinguish these restrictions, the spatial angle was changed in two ways. By changing the distance z between the plane of the object and the plane of the hologram at a constant area a, and by changing this area at a constant distance z. Transverse resolution is the minimum width of the object's details that can be resolved, that is, reconstructed, with the intensity of the transparent area between them at least 20% less than inside them. As applied to phase object, the value of the reconstructed thickness of the object varies within such limits. The smallest resolution attainable under the conditions of this experiment is the side of the test image pixels, or 156 micrometers, which corresponds to a frequency of 1.92 terahertz. It was found that phase reconstruction, which is more important than amplitude reconstruction in such significant applications as the detection of internal damage or hidden object, in pulsed terahertz holography not only has a resolution comparable to it, but also achieve a resolution comparable to the wavelength of the radiation used. In this study, contrast was defined as an expression on a slide. The first feature that needs to be mentioned is that the method of changing the spatial angle has the most significant effect on reconstruction contrast at the large values of this angle, while at its value of 0.04 steradians and frequencies below 0.5 terahertz, the curves the frequency dependencies of the contrast for the two methods of changing the spatial angle practically coincide. The second feature is that the reconstruction contrast at a constant z and spatial angle of 0.09 steradians is better than a constant a and spatial angle of 0.16 steradians, which is completely different from the form of the same dependencies for the resolution. This phenomena shows how important the number of pixels used is to obtain good contrast. The results of studying the longitudinal resolution of phase objects, or the accuracy of reconstructing their thickness, show that three-dimensional phase objects can be reconstructed with a transverse resolution of less than 2 wavelengths, and a sub-wavelength longitudinal resolution, even from the holograms, with a rather small number of pixels, for example 128 to 128, recorded on a relatively small spatial angles, for example 0.16 steradians. Based on the results obtained, the following conclusions can be drawn. The contrast of an image reconstructed from a hologram, the spatial angle of which was changed by its area, turns out to be better than when the spatial angle is changed due to a change in distance. This is explained by the fact that in the first case, at the larger spatial angle, the hologram contains 4 times more pixels than in the second. However, the resolution of the image reconstructed from such a hologram does not undergo significant improvements, since it depends only on the number of Fresnel zones covered by the hologram, that is, from its spatial angle. In the course of numerical simulation, an almost perfect agreement was achieved between the obtained and theoretical dependence of the resolution on the spatial angle. In conclusion, it can be said that the resolution and contrast of the object images reconstructed using pulsed terahertz holography have been rather thoroughly studied. This technology exhibits exceptional but highly spatial angle dependent lateral resolution in relation to the wavelength. The achieved resolution is comparable for both amplitude and phase objects, provided that a sufficient number of Fresnel zones are recorded. The contrast of reconstruction of amplitude objects and the accuracy of reconstruction of the thickness of phase objects were studied using pulsed terahertz holography. The results obtained allow to conclude that this technique can be a very promising and functional tool for non-contact visualization. Thank you for your attention.